Good morning, ladies and gentlemen. First of all, I would like to thank the organizer for kind invitation to visit this beautiful conference. Let x1, x2 be ID random variables taken in an arbitrary separable Banach space, denoted by Sn and n partial sum, and S sub 0 is equal to 0 element by definition. Denoted by compound Poisson distribution, denote the compound Poisson distribution or generalized Poisson distribution as this operator series where mu to the power star chi is the standard convolution power. In what follows, we denote by tau of mu random variables with this distribution. The compound Poisson distribution with we measure mu equal to n distribution of the sum on x1 is called the accompanying Poisson law or accompanying infinity divisible law for the distribution of Sn. It's clear that this accompanying Poisson distribution is the distribution of randomly stopped sum at Poisson point, where P of n is Poisson random variables, this means 0, independent of the original sequence of random variables. Poissonization inequality. The equality was such form with constant, not depending on n. It's very important. The first result in this direction was obtained by Yuri Prokhorov in 1962. He obtained the following result. Let x1, x2, and so on be ID scalar random variables with symmetric distribution. Then for every natural m, the following inequality holds without any moment restrictions, finite or infinite paths. Moreover, this inequality is sharp in the following sense. The supernorm is taken over all n and distribution of x1 such that such equality is valid for all set A without 0. As a consequence, Prokhorov noted that this assertion is valid also for the expectation of hyperbolic cosine, since the Taylor expansion of this function of hyperbolic cosine consists of even degree power function only. It's clear this result can be generalized in such a way for any entire function, for any entire function with non-negative coefficient with even subscripts in the corresponding power series, under such moment restriction, of course. In 1958, Sergei Udiev obtained the following generalization of Prokhorov's result. Let x1, x2 be ID random variables taken various in separable Banach space with mean 0, not necessarily symmetrically distributed. Let f be smooth functional on this separable Banach space such that f is twice continuously differentiable in the Frechet sense, and the second Frechet derivative, or the second Frechet differential, is convex functional in x for all fixed direction h. Under some minor restriction on this functional, would have proved the Poissonization inequality. This is a serious generalization of Prokhorov's result. I would like to note that the original proof by Sergei extends a few pages. He use the Kemperman's technique for obtaining low bounds for moments of sums of independent center and random variables here. Next, denote by G and such expectation. Assume that this function is well-defined for all natural n. We say that this function is convex if the one-step difference is non-decreasing function, and respectively concave if non-decreasing. It was noted that Poissonization inequality, one, is valid if G of n is convex function. Okay? This immediately follows from classical Jensen inequality. So the condition of theorem 2 by Utif imply convexity of this function. The inverse implication is false. The proof of this result extends a few lines. I would like to demonstrate it. First of all, we use Taylor formula. With probability interpretation of the zero term, Cauchy term, probability interpretation standard representation, where z is a random variable with a triangle density function on the unit interval, which is independent of the sequence here, of course. After averaging of both sides of this inequality, the first term vanishes. This is a continuous functional of centroid random variables. Okay? And we have this equality. We replace the summand with the subscript n plus 1 by the summand with subscript n plus 2 with the same distribution. And use Jensen inequality, we add xn plus 1 here by Jensen inequality, centered summand. Okay? That's all. So we have Poissonization inequality under this condition. Sorry. That converse application is false. Counterexample. Let xi be id real-world random variables with mean 0 a finite fifth moment. We consider power function for the 5. Okay. In this case, the second derivative is not convex on the whole real line. On the other hand, the function g can be represented as quadratic trinomial with respect to integral value of n. So if the third moment is non-negative, this parabola is convex, otherwise it's concave. In other words, we have upper and lower Poissonization inequalities independent of the sign of the third moment in this example. Now we consider the so-called Poissonian setting, where the summand is equal 0 with positive probability. For every non-negative measurable functional f, the following inequality hold. Poissonization inequality. No, I would like to note that this result is very simple. It follows immediately from two facts. The first one is the so-called Hinching representation of the sum distribution. In the Poissonian setting, we introduce auxiliary sequence of random variables with such distribution. And Hinching proved for a real valued case, of course, the following representation. The original sum is has distribution coinciding with the distribution of randomly stopped partial sum as 0n. This random variable has the binomial distribution with parameters n and p. And a similar representation is valid for the companion Poisson law. I would like to note that this representation is valid for any measurable abelian group, not necessarily linear spaces only, not necessarily real valued case as in Hinchin's paper. And the second result is the upper bound for Radon-Nikodym derivative of the binomial distribution with respect to accompanying Poisson law. There are many upper bounds, but I prefer the first one, since in the real Poissonian setting, this value p is sufficiently small as a rule. From these two results, we deduce this inequality without any problems. It's a student's exercise, in fact. We'll consider some application to empirical measures. It's a multivariate application of the scheme mentioned above. Denoted by P star, when the empirical distribution based on the sample of size n from taken values from size n from arbitrary distribution in arbitrary measurable space. Introduce the empirical count and measure. This measure has the structure of the sum of random processes indexed by element from calligraphic A. Okay? We will consider such processes as random elements taken values in Kolmogorov space, the space of all function indexed by element from an abstract set, endowed with a cylindric sigma field, standard Kolmogorov space. We need no assume here Banach space structure of the sample space. The companion Poisson distribution in Kolmogorov space for empirical measure is this Poisson point process, randomly stopped sum. Okay, P of n is a Poisson variables with parameter n, independent on the sample observations. It's well known the main property of Poisson point process. For any P with disjoint subsets, the random variables, the corresponding random values of this point process are independent. They have the Poisson distributions with respective parameters. For empirical measures, we can study Poissonian setting as well, the so-called scheme of restricted empirical measures. Let I 0 is an arbitrary measurable set with positive probability, less than 1, of course. Consider the restriction of these random point processes to the family of all measurable subsets of this measurable set is 0. In this case, we deal with the random processes indexed by element from this new restricted family with, under some restriction, probability this random element is equal to 0 element in Kolmogorov space with positive probability. So we can use Hinchin representation and Radon-Nikodym derivatives, upper bound for Radon-Nikodym derivatives. We obtained following inequalities and for expectation of non-negative measurable function as well. A few words about coupling. What does it mean, coupling? If two random variables defining common probability coincide with probability, non-zero probability, no, maybe close to 1, we say about coupling. First of all, I would like to recall the famous, remarkable result by Dobrushin, proved in 1917. Any random variables taken values in separable metric space, one can construct, can be constructed on a common probability space such that probability of their known coincidence is equal to the total variation distance between the distributions. This result is, in fact, complete solution to the famous Kantorovich problem for the indicator metric. Indicator metric is 1 if x and 0 is the opposite case. So this probability is the expectation of such distance. This result, duality theorem for Kantorovich mode problem in this particular case was proved by Strassen in 1976. And Dobrushin constructed explicit form of this optimal point, of optimal couple. Explicit algorithm to construct these optimal points. From this result by Dobrushin, Hinchian representation and well-known result on accuracy of Poissonian approximation to binomial distribution, we deduce the following result. In the Poissonian setting, the random variables Sn and randomly stopped S can be defined in the common probability space so that the probability of non-coincidence, these two elements, less than probability non-coincident for binomial distribution and binomial distribution in Poissonian accompanying distribution. And Hinchian representation S0 binomial distributed random variables. Analogous representation is valid for. And this event implies the event. And we choose here the optimal construction from Dobrushin's theorem. And the right-hand side of this chain of inequalities is the upper bound proved by Barbour and Peter Hall for the Poissonian approximation of binomial distribution in 1984. Corollary to the alpha zero restricted point processes, nu and E Poisson point process can be defined in common probability space with this probability of non-coincidence. I would like to know the scheme of local empirical process, very popular scheme of 1990s, is a particular case of restricted empirical process mentioned above. Now, I would like to study Poissonization inequality for some class of additive functionals. Let delta 1, delta 2, and so on, finite or countable measurable partition of the sample space. Denote by nu in, the corresponding value of the empirical normalized measure. Our goal is to obtain moment Poissonization inequalities for such additive functionals. And under the restrictions, only such restrictions. No examples, the classical square statistics has the form. If we consider indicator type processes, we deal with such functionals. The number of cells, each of them contains a number of sample points from the range defined by the set A. This popular model since the pioneer paper by Bahadur. Let f be an arbitrary non-negative finite convex function on R, and let all the function f in be non-decreasing, or all of them are non-increasing. Then the following Poissonization inequality holds, where by in independent Poisson random variables with the same mean as the random variables nu in, and the constant C0 admits the simple upper bounds of such a kind. I would like to note this series is well-defined you the Borel-Cantelli lemma. If the functions have bounded variation at all finite intervals, then each of them can be represented as sum of monotone function. Monotone function, and we can reduce the problem of bounded of expectation of this functional to the case mentioned above for monotone function. Now, in particular case, f equal to exponential function, we can estimate the tail probability for such functional using the minimal exponential Markov inequality, standard tool to investigate tail probabilities for sum of independent random variables, beginning from pioneer paper by Sergei Bernstein in 1911. And this expectation one can replace with the expectation of Poisson point processes. We can reduce the problem to analysis of independent random variables. Now, as an example, consider the additive function with the following non-decreasing function. In other words, nkn is the number of cells containing at least k plus 1 particles after n tosses. Using the minimal exponential Markov inequality, we can obtain exact upper bound for probability of such a kind with implicit constant. The Poissonian mean function mkn admits the simple representation as sum of in terms of gamma function. In particular, for such distribution of heating the cells, we have this asymptotic for this mean function in terms of integral of gamma function. And now we can substitute this asymptotic to the right-hand side of this inequality. Okay? And choose sufficiently small r tending to 0 in accordance to such asymptotic of mean function mkn. For example, for k equal to 0, this number is has such asymptotic, and we can obtain the tail probability for number of occupied cells in this multinomial scheme. For additive functional without monotonicity of function fin, one can obtain Poissonization inequalities using analogous inequalities for restricted empirical point processes. Namely, we divide the series in definition of additive functional into two parts. For each of two sums, we obtain the optimization, Poissonization inequalities of such kind, using the scheme of restricted empirical processes for the first sum, restricted to the set A0, for the second one, restricted to the complement of this set. Well, for example, if we consider non-negative, non-decreasing convex function, like exponential function, we can obtain for this general additive functional such Poissonization inequalities up to this factor, to absolutely the same, with such implicit constant. In conclusion, I note that Poissonization technique is popular to analyze empirical process, local empirical process, additive functional for the indicated up functions. This technique was used by Darling, by Carlin, and Bahadur as well. That's all. Thank you very much.